Welcome back to part 2 of our video series on section 2.5. We're doing function transformations. In this section we are shifting, stretching, squishing, flipping functions around so that we're kind of playing with the graphs and we're seeing what we need to do to the function equations to create those outcomes in our graphs. So in the first part of this video we talked all about shifts. So vertical shifts up and down, you add or subtract outside the function. For a horizontal shift, left or right, you add or subtract inside the function, and you kind of do it backwards. So in this part of the video, we're going to talk about stretches and squishes. So I want to start with f of x equals the square root of, let's do 3 square roots of x. Yeah, this is where I want to start. So once again, I'm going to make a table of values. The 3 is happening on the outside of the function, so I can have my table of values look like inputs, the function, then the transformation. So the base function is happening here. So wherever the base function is happening, that's where I want my 0, 1, 4, 9. That's where I want the standard inputs to go. And I know what happens to these standard inputs under the base function. I get 0, 1, 2, 3. So to get this, I'm just going to take all these outputs and I'm going to multiply them by 3. So I get 0, 3, 6, and 9. They are 3 times bigger. And hopefully that makes for a really easy graph. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I have 0, 0. I'm going to graph the base function first. I have 0, 0, I have 1, 1, I have 4, 2, I have 9, 3. This is the base function, y equals the square root of x. The transformed function is going to be 0, 0. It's going to be 1, 3. It's going to be 4, 6. Here. And it's going to be 9, 9. So this function this is different from our shifts. When we took our graph and we shifted it, the entire thing moved by a set amount. So like the entire thing moved 2 units up, or the entire thing moved 3 units to the right. That's what we did when we were shifting it. This isn't behaving that way. Like this point is on both. This point hasn't moved at all. This point went up 2, this point went up 4, and this point went up 6. So there's no one fixed number that we can add that will account for all of this. But what did happen here is this height got 3 times taller compared to this. And this height got 3 times taller. And this point didn't move because making 0 3 times taller still gives you 0. So that's what's happening here. If you put a 3 in front of a function, you get something that is 3x taller. So hopefully we can imagine what happens if we do something like g of x equals 1/2 square root x. I'm going to erase some of the pieces in here. If you put a 3 in front, it makes it 3 times taller. If you put a 1/2 in front, it should make it half as tall. So you'd have a point here, you'd have a point here, and you'd have a point here. So this is y equals 1/2 square root x, and this is y equals 3 square root x. So this is half as tall, or sometimes you might say that this is 2x shorter. This kind of transformation is called a stretch. This is a vertical stretch. This vertical stretch. I left my one hand still when I made that first stretch gesture, but it was off the camera, so you couldn't see that. It looked like a shift. It's not a shift, it's a stretch. The official word for this is a compression. But that's a boring word, so the word I use for this is squish, which I can spell. There's not a G. I call this one a vertical squish. Makes it shorter. So, let's talk about horizontal squishes and stretches. Just like in the last video, the vertical transformations are what happens on the outside of the function, and the horizontal transformations are what happens on the inside of the function. So if I want to create a horizontal stretch or squish, I'm going to try something like 3x squared. So we're going back to the parabola. So the square root, I think the parabola is easier to illustrate what's happening here. So for this one, I'm going to do sort of the same thing we did before. I want a 3-column table, but the transformation happens first, and then the base function happens. And just like before, these are the numbers that I want to be working with here. I want this to be my -2, -1, 0, 1, and 2. And then when I square these numbers, I'm going to get my standard 4, 1, 0, 1, 4, the standard spread there. But just like when we were doing a horizontal shift, when you start in the middle with the numbers that you want to hit with the function, the squared, that means that you have to work backwards to get to your original inputs. So if 3x was -2, that means that the original x I started with needs to have been -2/3. So to get backwards to here, I need to divide by 3. And if 3x is -1, that means that x must be -1/3. I have to move backwards and divide by 3. If 3x is 0, that means x is 0. That one's nice. Easy to divide by 3. If 3x is 1, that means x was 1/3. Dividing by 3 there. And if 3x was 2, that means that x was 2/3. So we can make this graph 1, 2, 1, 2, 1, 2, 3, 4. As usual, I'm going to start with the base graph as 0, 0, a couple 1s, and then 2, 4. So this is the base graph. The transformed graph hits its vertical 4 at -2/3, hits its +1 at -1/3, hits 0 at 0, that hasn't changed. This is +1/3, and this is +2/3. So this is y equals 3x squared. This is y equals x squared. So as usual, base function is in a solid line, the transformed function is in a dotted line. I probably should be doing that backwards, but I kind of started it this way, and now I'm stuck. So let's talk about what happened here. We multiplied the inside by 3, and the function that we got out is squished. Whatever this distance used to be, this new distance is 1/3 the size. Whatever this distance used to be, this new distance is 1/3 the size. Same thing down here. This distance got cut in thirds. So we used to have a big horizontal distance here, now we have a tiny horizontal distance. We used to have a big horizontal distance here, now I have a tiny one. Putting the 3 on the inside created a horizontal squish. This got 3x thinner, three times thinner. I probably shouldn't use x as times when x is a variable right here. This is 3 times thinner. This is 3x, the variable. So hopefully we can imagine what happens if you do f of x equals 1/2 x squared. Actually, let's not imagine it. Let's just do it. Make a new table here. X 1/2 x 1/2 x squared. As usual, the base function happens here. So I want to start with these numbers, -2, -1, 0, 1, and 2, which squared gives me 4, 1, 0, 1, and 4. So if 1/2 x is -2, that means that x was -4. If 1/2 of this is -1, that means that the original is -2. This one was 2, this one was 4. So to go backwards, I have to double these numbers. Didn't leave myself enough room for this, but we'll try. We'll try to put this over here. Squeeze that in. Okay, so I'm all the way back at -4 by the time I hit this. I'm back at -2, 1. This point is unchanged. That's 2, and this is 4. This is y equals 1/2 x squared. This is gone. This is what I want to talk about. This is a horizontal stretch. This got 2 times wider. So we still have the same sort of like backwards seeming behavior showing up when we do these horizontal transformations. You'd think that multiplying by 3, which I just erased, it's easy to sort of assume that multiplying by 3 on the inside will make something wider, or that dividing by 2 will make something thinner. But it's kind of backwards. It works that way for vertical stretches. If you multiply something by 3 on the outside, multiplying makes it taller. Or multiplying by 3 makes it taller. Multiplying by 1/2 makes it shorter. So vertical stretches and squishes behave in the way you would expect them to. Horizontal stretches and squishes behave sort of backwards the way you would expect them to, just like horizontal shifts do. When you multiply by 3, it gets thinner. When you divide by 2 or multiply by 1/2, it gets wider. And that's still because when we make these tables, the base function happens in the second column, and the first column, the relationship between these first 2 columns is you have to sort of undo what has happened to the x value to get the original inputs. That's why if we want to be squaring the numbers -2, -1, 0, 1, and 2, you have to double the x values so that they start bigger before this transformation happens, and then they get squared. So that is my explanation for why the horizontal transformations all work sort of backwards from how you'd expect them to work. There's one more kind of transformation I want to talk about, and then I want to do a summary recap thing, and I think I'm going to put that all into a third video so that these are all pretty little bite-sized. 15 minutes seems like a good chunk. Stay tuned.